we have started this, one of the most important paradigms in this course, which is called the greedy paradigm. So best it will be seen is through examples. We'll do 3 or 4 examples. First is the job scheduling problem. So what you are given here is n jobs, J1 to Jn, with their start and finish time, and that has to be, and it is strict. So you have to start at, the server has to start job Ji at Si and has to finish at Fi. And if it cannot start at Si, then essentially the server has to skip the job. So your algorithm has to schedule these jobs, n jobs. I mean, all of them may not be, it may be impossible to schedule them. So you try to do the maximum. So to schedule the maximum number of jobs, this inherently is a hard problem because, or well, from the looks of it, it is a hard problem because it is like finding, it is like guessing the subsets of J1 to Jn and then trying what is the best, right? So the number of subsets is exponential in n. So what we will do here is, we tried many policies, right? So the first policy was that schedule the earliest one. So in this example, you can see that the one that starts earliest is either J1 or J3. So if you only look at the Si, then you might pick J3, which will block everything else. Its server will be busy only with J3, so this is a bad choice. Second policy is you look at the difference, so Gi minus or Si minus Fi. So first was just Si, policy 2 is Fi minus Si. The minimum one you pick with the understanding that if job Ji is taking the shortest duration on the server, then maybe it is best to do it first. But for some reason, you can see here in the example that this will mean scheduling J1, J9, J7, which is still not the maximum. So maximum is obtained by policy 3, which is you schedule the one that will finish earliest, so least Fi. Okay, and we have shown, well, we want to show now that this policy 3 is the best, in the sense that in policy 3, so lemma 1 will not claim that every optimal solution will follow policy 3, but lemma 1 will just claim that there is some optimal solution which follows policy 3, okay, which is good enough. So that is what we want to show, that if x is the job with the least f of x, finishes earliest, then there is an optimal solution where x is scheduled. Any questions till now? Okay, so let S prime be some other solution, optimal solution, with y being the first job. So this may not be okay, so this is y is the first job instead of x. So what we will show now is that if f of y is above f of x, then we can improve on this, or we can at least change S prime to S. Okay, so we'll transform this to S without decreasing the number of tasks scheduled. So let us do that. So what this property means is f of x is less than equal to f of y. Is that clear? Because f of x was what was absolutely the minimum finish time. Any other job y satisfies this inequality. So in terms of the diagram, what it means is, so this is the time scale, and so x definitely finishes first, while y may finish at the same time or a bit later. Okay, this is what we have. So x finishes first and y may finish at the same time or a bit after x. So do you see how you will transform S prime to S? How will you schedule x? By making a minimal change in S prime, the schedule S prime. Well, it's actually almost obvious. So what you have to do is, we can replace y in S prime by x. Why is that? So in other words, we can define S to be S prime minus y union x. We can swap, we can replace y with x and get this schedule, which will still be a valid schedule. Why is that? See, so y is the very first job which S prime has. So when you remove it, what remains? So S prime minus y is a valid schedule. There is no conflict. Now when you add x, x will be finishing before y finishes. So this will not conflict with whatever is there in S prime minus x. Okay, so none of these are conflicting. So this is a valid schedule. Also, x doesn't conflict. With anything there. Right? It doesn't conflict simply because it finishes before everything that is in S prime minus y. Because x finishes actually before y. So it will not conflict with anything else than y in S prime, right? So this means that S is also a valid schedule. And what is the size of S in S prime? It's equal, right? So it's an equally optimal schedule. So we are done. Is that clear? So if S prime was optimal, then by the size argument, S is also optimal. And we have already shown that S is actually a valid schedule. So we are not really making a mistake. We are not introducing a conflict in the schedule. It follows all the input assumptions. So any optimal solution which doesn't have X can be transformed to have X and still be optimal. Okay? So these are the tricky things that you have to first discover and then you have to give a proof. Okay, otherwise we won't accept it as a greedy algorithm. So this looks very simple when you read it, but it's not easy to come up with these arguments. So at this point we can then define J prime to be so J was the jobs given in the input. So let us remove the ones which contain X, which overlap with X, sorry. Okay, so we had defined, recall we have defined this overlap J comma I. So these are the jobs in input J that overlap, whose S comma F interval overlaps with I. So basically K and I cannot be simultaneously scheduled. If a schedule has both K and I, then there is a conflict. Okay, this is an invalid schedule. So once we have scheduled X, so overlap J comma X are the ones which are now invalid jobs. They cannot be in the same schedule. So let us remove them from J. Let's look at J prime. Okay, this will be the next step. And now what is the property? What is the optimal schedule size for J and J prime? What is the relationship? How do they relate? What is the relationship? So whatever is the optimal of J prime, in that you can always introduce X, right? Because nothing in J prime overlaps with X. So whatever is optimal of J prime, you can introduce X, so it's +1. And so optimal of J will be at least this much. Clear? I'm not yet saying they are equal, but this property is certainly there by removing the overlap. Since X doesn't overlap with any job in J prime, we can add we can schedule X with whatever is the optimal of J prime. Okay, so whatever is the schedule of these jobs J prime, X can always be scheduled with them. So optimal of J prime +1 is the, or maybe I can put size there. So the size of the optimal schedule of J prime +1 is a lower bound on our answer. Okay, this is correct. Any questions till now? So we actually want to show that these two are equal. So which means if we can show that optimal of J prime is, or in other words, if we can show that optimal of J is less than equal to optimal of J prime +1, then they will be equal. Right? So that is what we will show next. So for X S J prime as above, we'll show that optimal of J prime is greater than equal to optimal of J minus 1. And optimal of J is in lemma 1 we were assuming that to be S, we are calling that S. So this is essentially size of S minus 1. Yeah, this again will be very simple. You may be confused with the multiple inequalities, but so how do you show that optimal of J is less than equal to optimal of J prime plus 1? So we want to, in other words, show that optimal of J prime is at least optimal of J minus 1. This again is the same thing as we used before, the same property. So you replace S with S prime by introducing X, and then you delete X. Right? So that is a valid schedule for J prime, and so optimal of J prime will be at least as good as that. So like lemma 1, consider S prime which is S minus so S has X, so remove X. So consider S prime S with X removed. Clearly S prime is a valid schedule. Of jobs J prime, which means that optimal cannot be worse than this. So optimal will be at least this size of S prime, which is size of S minus 1, which is optimal of J minus 1. Okay, so we have shown both the sides, both the inequalities. It's essentially the same proof, but you have to write this clearly, because only now you can say that by both these lemmas 1 and 2, optimal of J is equal to optimal of J prime plus 1. Okay, so this will give us the algorithm. You basically find this X, remove it, define J prime. For J prime, find the optimal in recursive or iterative style, and then add back X. No, less than equal to is shown above. So what these two lemmas or properties tell us, it's actually the same property, but you want to be clear about this. So the two inequalities imply that it's actually the two things are equal. Okay. So then, yeah. So this this directly gives us pseudocode now. So let us write that. We will call it schedule J comma n. So so this is the input, j with n jobs, and you are given this, j means also that you are given s comma f for every job. So how will the algorithm start? This greedy algorithm? It is greedy because it is finding the jobs one by making a local decision. Okay, it doesn't care about all the jobs, but it only looks at this x. And then the rest it gives to the next while iteration. So what you have to do here is look at the policy 3. Policy 3 is that you have to find this x, which is the earliest finish. Right? So we find that, then we define j prime, and then we go to the next iteration. So we have this temporary set A, which will find the correct jobs, schedule the jobs one by one. So let's do that. So till there is a job left unscheduled, what we'll do is we'll find this x with min finish time. And we'll put that in the temporary variable A, the variable which is basically a set. We'll store this. And what will you do with j? When you have identified x in j, then you should remove all the jobs in j which overlap. Okay, and with this, the while loop continues. So find an x with min finish time. I mean, there will be many jobs which have the same finish time, but you can just pick one, and output that and delete the overlapping jobs, because the overlapping jobs can never be scheduled with x, right? So reduce the j, which was your input, and then go back and see whether j has something remaining. Schedule the best, output that, and then proceed. So in the end, you will get the schedule A. So that you return. Is it clear? So this is the very short, simple pseudocode to solve that hard problem. So how fast is it? So how many iterations of while? Well, in the worst case, it will be n. Every time you are deleting only one. So iterations can be n, and the time also is n, because you have that, I mean, you have to find the min first of all. That is at least n. And you have to also find the ones which are overlapping with x. So that is also n. So this is n square, right? So is this, if you implement it naively, then this is n square. But of course, we will not do it like that. We will do it much faster. So how fast can you do it? Can you implement this in linear time? Yeah, so it is not clear whether we can do it in linear time, but we can do it like sorting. So n log n. But then I have to specify what the implementation is. How are we finding min? Because if we are finding min by a scan, then that will be linear time. So how do you find min? Can you think of a data structure after so many months, weeks? Yeah, use heap. So let us add that here, that implementation has to be careful. So we can store J as a heap. As a min heap. So I'm skipping the min. Store J as a heap, and the key is, what's the key for sorting? Sorry? The finish time, yeah. With key the finish time. And for this you will do extract min. Okay, so this min finish time job X has to be found in the min heap, where the key, I mean, you have again multiple options, right? There were many policies, SI, FI, F minus S. So the one we have picked as key is F. And with respect to that, the heap is maintained and you extract min. So extract min is log of the size of J, so log n. So that problem is solved. Now we come to the other problem, which is more complicated. How do you find these overlapping jobs? Because heap doesn't have a inbuilt function for this. So how will you find in the heap the jobs Y which overlap with X? Yeah, but even that can be n. Maybe all the jobs overlap with X. Right, that is, there is no guarantee. So, so here we cannot be greedy. We cannot say that do this in log n time, because there may be n by 2 jobs, for example, which overlap. So you have to go through n by 2 jobs one by one. So let us just do that. So delete all the jobs. In the increasing order of start. From J. So this also we can store. We can have another heap where we have the key S and, well, I shouldn't say heap actually. This maybe you should store in an array. You can store the, no, maybe I should first ask you, with what you see these ideas, what is the time complexity now of the pseudocode? First step, we have made log n. Second step, we are saying whatever there is, you keep deleting it. And that can be order n. So why is this still not order n square, n times n? Exactly. So the thing is that if in one step already you have deleted n by 2, then those edges are, those jobs are gone. Right. So overall, if you look at all the while iterations, overall there are only n jobs to be deleted. So it's not n square, it's still n. Is that clear? So that is the main thing you have to understand, and then hopefully you can complete the proof. extract min and this delete job. Or delete just one job. Takes order log n time. In one call. Okay, so in any heap, when you do extract min, we have seen that it takes log n time. Also, if you want to delete some node in the heap, right? So for that, what you can do is you know this primitive function of decrease key. So you can decrease the key to -infinity, so it comes at the root, and then you can extract min, right? So that is the deletion. So both deletion and extract min, one call can be done in log n. And then when you are finding all the overlaps, so this j minus overlap, this across all while iterations, calls delete job how many times? Well, there are only n jobs, so only n times. So order n times. So which means that its complexity is overall order n time, n log n time. Is that clear? So your single calls are called extract min and delete job. They are very fast, log n time. And how many times are they called? That is limited by n. So you have to see not just one iteration of while, but across all iterations. Okay, so across all the count is correct. It gives you n log n. So this is a very clever algorithm at many levels. You have to discover the key with which you want to be greedy. Then you have to give the proof, and then you have to give the correct implementation, which is using heap. Right? So every part of this code is highly clever. You will not be able to do this in the first attempt. Any questions? Okay, so then we move to the next problem, which is even more important. So this is called the spanning tree problem. So this is the second example of greedy. First we did job scheduling, example 1, this is example 2. So what do you want to do here? Have you heard the spanning tree problem before? So you are given a graph, undirected graph where the edges are weighted. So it's basically a connection of let's say cities through roads or rail, right? So you have these roads with some distances assigned. What you want to find is a tree structure which has minimum weight and which touches all the cities. Okay, so you want to find the minimum road network in terms of distance, which covers all the cities that you are interested in. So think of a road or communication network . So in fact, even without weights, you can think of this question first. So these are the 4 vertices, and then you have these edges. So the question is, what is the least? What is the least number of edges to maintain connectivity? So the answer is, in this case, you start with 7 edges. What is the minimum number of edges which will still maintain connectivity? 5, right? Because the number of vertices is 6. And you know by your experience and exercises that if you have n vertices, then n minus 1 is the size of the tree, if it exists. It always exists when the graph is connected, like here. Right? So for 6 vertices, 5 edges are enough. So the 5 edge one is, just pick some tree. Okay, so for example, this is the subgraph G prime. So it has vertices are the same, edges are fewer. 2 have been deleted, but yet this graph is connected. So this is the minimum edge subgraph, which keeps the graph connected, the vertices connected. So this is a tree. So this already is a problem, finding the tree in a given graph. How do you solve that? Yeah, so you have seen multiple algorithms for trees, DFS tree, BFS tree, right? Just use those trees. So BFS, DFS already gives this. So that problem is a solved problem. In linear time, you will get it. But this is not the practical problem. The practical problem is you are given roads or communication networks where there are weights or cost on the edges. Right? So cost, BFS and DFS will not be able to use. There was a similar problem in one of the quiz where there was cost associated. But that algorithm was very slow. It depended on the cost. So now we'll do something this week, and then the next week we'll do something much, much faster. So we change this problem to the more realistic problem. So in reality, we need a cost on the edges. Right, so that is our input output now. So in the input, what you are given is undirected graph. With a weight function. So it's W, which assigns to every edge an integer. That's the new component in the input. Okay, so graph is given with a function, which is just, I mean, if you don't want a function, you can just think of the edges having numbers written on top. Okay, so That is what this function is giving. These integers can be negative or positive. We will not worry at this point about their sign. And what is needed in the output is a spanning tree G prime. So this is the definition of spanning tree. Should have written it before. So this is called the spanning tree. It's just a tree which is n minus 1 edges, and it goes over all the vertices. So you want a spanning tree G prime whose weight is minimum. Such that the weight of E prime, so weight of E prime is defined as the sum of the weight of each edge. This you want to minimize. Okay, so again, this question is a hard question a priori, because it is asking you to find a subset of the edges. Number of edges was m as always. So by definition, what it is asking is you have to find this E prime of size n minus 1. It's a subset of m edges, and across all such subsets, this sum should be minimum. Right? So it's clearly an optimization problem where the answer is a subset. So the way it is stated, but just looking at this, it looks hard. So again here, this is there is no easy brute force way for this. So finding E prime subset of E could take, so m choose n minus 1, right? And this is, if you know the binomial estimate, this is around m by n to the n. So m is around n square, or even if m is around 2 times n, this is still 2 raised to n. Right? So this is an exponential number of subsets that you are trying to find necessarily. So this, it could take these many steps to optimize weight. Okay, so the question is, can you do it faster? And for this, there is no easy idea. So you can do this brute force implementation, or something other than brute force implementation is completely unclear, right? So what we will do is we'll use the greedy paradigm and give a very fast algorithm for this. Okay, so let's make some simple observations first. So a spanning tree has number of vertices minus 1 many edges. We've already meet that observation. And second is that adding an edge in G prime does what? So in this, in any spanning tree, if you add an edge, how will the graph change? It won't be a tree, first of all. Since it's a spanning tree, it's not a smaller than spanning tree, it's a spanning tree, so this is actually a maximal tree in some sense. So if you add an edge, it stops being a tree, which means there is a cycle. So how many cycles are there? Yeah, there is a unique, so adding an edge in G prime gives a unique cycle. So let's say you added E, adding an edge E in G prime creates a unique cycle which involves E. Okay, so there is a unique cycle. Moreover, that cycle involves the edge that we have just added. That has to happen because if it doesn't involve E, then it means there was a cycle already, right, which is a contradiction. So this edge that you have added, that has created a cycle, and that's a unique cycle. What is the proof of this? Why can't there be two cycles involving E? No, because it was a tree. Why? No. It can add n. It can add any number. What is the proof that it will add only one? Exactly one. Yeah, that is a description of one cycle. Why is there no other? So, as a warm-up, you should prove this because we'll be doing such things in the algorithm a lot. So these are the observations. Nobody confuses them. They are very believable, but you should also rigorously prove them. So now, using these, how can we be greedy?